So you are interested in compressed air systems and NSIs, that's great. So let me introduce you to what we're doing. This is a set of compressors running in a factory. You have the inlets and you have a common flow for the system. This typically goes to the different parts of the factory where you have production. You have some certain pressure that you typically set for the factory. Now, how do you design this type of system? Well, typically you work a little bit like this. This is sort of the flow range where the factory works. Sometimes they work a lot, you need a lot of air. Now we're here. They work a little, now we're over here. And you want to design the compressors to actually produce the amount of air that you need for a certain time. So this is a typical way of doing that. You thought of it a little bit like Lego or Tetris, if you like that you take the sort of amount of air that each compressor can supply and you add them on top of each other, and you try to actually match what you will actually get to what you would like to have. And you see here that when I'm adding these together, they're not exactly following the diagonal here, which means that they don't get the amount of air that they actually want. Here they get a little bit too much. So what happens then? Well, basically the pressure starts to fluctuate, the compressors don't work all right together. It can even be in other situations, even if you manage to design this in a good way, appropriate for the factory, still the compressors don't run because they are not cooperating with each other in a good way. And furthermore, this doesn't give you any quantitative information about how bad is the system, what is the inefficiency. And that's what we want, right? We want to see how to improve the efficiency of the system. Another way of doing this could be something like this, just to show you. Some compressors, in this case number 1 here, has some regulating capacity. So you can actually give some more air, some less air, and do it in a rather efficient way. So here I'm indicating that with this line here, that you have some air here, like this. This is the flow. So the further out here, the more flow you can get. So this compressor doesn't give very much as a base flow, but you can regulate it up to a lot. Number 2 doesn't have any regulating capacity, and neither does number 3. So you add these together and you take the non-regulating capacities, you get here, and then you add the regulating capacity like this. It's very similar like this. Here you have the regulating capacity in the triangles here, but basically it's the same way. I'm going to show you a little bit how to use this information to actually calculate how inefficient a factory is compared to what it could be if it was running the compressors and the system in a good way. Thank you. So, looking at sort of the energy savings of a factory, you want to understand a concept called SEC, specific energy consumption. It has the unit of energy per cubic meter. Sort of how much energy do you need to produce 1 cubic meter of air that is later used in the factory. So this is one way of putting it. It's the derivative of the power to the flow. And what we can do here, we can look at one of the compressors from our example here and see how it performs over various flows with respect to the SEC parameter. And you can see it has some curve here, and then it's actually flat. And the reason for this is that the number 1 compressor was actually regulating. So once it reaches some basic flow here, it will be able to sort of increase energy as it increases the flow, and this creates this sort of constant SEC, which is very useful in factories. But these compressors are more expensive, of course, so you need to use them in a good way. Now, we didn't have 1 compressor, we had 3. So look at this example here, where you see there are actually 3 curves, where I've added, here I'm only running number 1, here I'm running number 2, and number 1, here I'm running all 3 compressors. So I indicated with the different colors here, and you see, so what happens here is when I start from a low flow, and the flow is increasing in the factory, I'm just running number 1, and maybe at some point I want to turn on number 2 because I need more air. Then it jumps up the energy consumption here per cubic meter and goes down again. And at some point I need even more, I turn on the last compressor. And here, maybe I go into a flat region where I have the regulating capacity working. Maybe this is not the best way of doing it, but it's an example. Here we can create like a reference curve for the SEC, like the black one here, where you see there are some bad places here where if we actually produce air like this, the specific energy consumption will not be that good. So this might be something to look into. Okay, so typically when we go to a factory and do the analysis and look at how they operate the system, these could be measurement points. So they could actually be quite far from the optimum situation where you sort of have the lowest power consumption per cubic meter. So maybe it will look something like this. I'm indicating sort of measurement points. The way we actually measure the SEC and we measure the flow, and we get these points here. And here you can see that, well, maybe these points sort of seem to belong to this curve here, and probably these points belong somehow to this curve. So we can do association like this and understand how the system is operating. But you can clearly see here that there is a huge difference in this case here between the measurement points and the reference curve, indicating that there is a big delta SEC, a big delta in what we can actually sort of reduce power consumption. So this is a quantifiable measurement of the inefficiency of the factory. You might have seen the energy savings equation I had before. This is it. We're actually taking the SEC at every flow, at every sort of second or minute that we're calculating, and we're integrating that into the total energy savings for a particular factory. And how do we do that then? Well, we look at this type of diagram, for instance, where you have SEC versus time, and you can see that at some point in time here, energize comes in and starts saving energy for the factory, so the SEC is actually dropping. But if it was running as usual, it will behave like this. And this is quantifiable. We know how the factory was operating. We know what it was doing before, so we can actually create these curves and we can get a measure of the difference, the delta SEC. And we can use that to calculate this value and get a quantifiable measurement of the energy saving we are performing. And even before we start, this is what you will get. So this is likely that you will get. And of course, there's much more to say about this. For instance, using the method I've sketched out here, it's actually possible to use even before you start building the system. Or if you need to buy a new compressor because your factory is changing or something, you can actually use all of these methods to like simulate how it would operate if it was actually running for real. So this is sort of, and it also gives us sort of the possibility to optimize, because if we can put the computer software to do the calculations for us, then we can get all of these numbers automatically, and we can, by using that kind of information, we can automate the analysis and make it much more advanced. It's like a base plate for the future calculations and advanced measurements and the sort of feedback that we can give to the customer, and actually try to use all of this information to replace the engineers that are typically trying to tear their hair and trying to get the system working. Here we can get real information that is very useful directly. Thank you very much for listening.